All right, good morning, everyone. So, what I'm going to talk to you about today is how to run the biggest node on the network, how to run a big node on Lightning. I am Bastien. I'm working at ACINQ on the Lightning specification and our implementation Eclair. So this you'll see that this may be disappointing, but it's actually not that hard to run a big node on the network today. It's it's not rocket science. It's just about making good architectural decisions and informed and reasonable engineering choices. All right, so for the scope of this presentation, what's nice is that I don't need to explain a lot about Lightning. The only thing I need to tell you is that Lightning is a peer-to-peer network where all of these connections between nodes are persistent connections that require unchained transactions. They're what we call channels. So this is, you don't need to know anything more. How can we be a node on that peer-to-peer network that handles a lot of these persistent connections, basically? All right, so who we are in that network is the ACINQ node right here at the top in the number of connected connection count. So we've been there for a while, and I'm not sure we're gonna stay there eventually because many people are coming with a lot of liquidity, running bigger nodes than we do, and our goal is definitely not to always be the biggest node on the network. This is not reasonable, and also people are going to be screaming about centralization. We are a big node, it's horrible. But actually, it's not that horrible in Lightning because everything is source routed, meaning that the sender decides where they want to go in the network. So if they don't want to go through our node, they can just route around it. It's not an issue. There's no such a centralization issue in Lightning as there is in Bitcoin mining, for example. So, and in the long run, you cannot prevent wealth from not being evenly distributed. So some nodes will have more capacity than others just because you cannot compete with, if you're an individual, you cannot compete with a company running a node and having a lot of money to pour into it. But what's important is that there are enough of these big nodes so that you can choose among many routes to be able to avoid going every time through the same hub. All right, so I was trying to impress you with those figures, but clearly that's not that impressive, so maybe I have to explain what it means to run a big node and where the challenges are. So there are scaling bottlenecks in Lightning. What I mean here by scaling is not necessarily scaling the network or number of payments we do, but how do you scale an individual node to be able to relay a lot of payments, to have a lot of channels without degrading the quality of service. So some of the important aspects to take into account are, first of all, the number of connections. You are basically a node on a peer-to-peer network accepting TCP connections from potentially anyone. So obviously, that introduces some denial of service risk. So you have to be mindful of that. You cannot have an infinite number of sockets on one server. You cannot have an infinite amount of bandwidth fuse. So you have to somehow protect against that if you want to be able to scale to have many connections. There's one very simple way of degrading the quality of service. If you are overwhelmed, you can just restrict TCP connections to people you already have channels with, because since channels require an unchained transaction, that's an inherent protection against denial of service. People need to make an unchained transaction to be able to have a persistent connection with you. So that ensures that those people need to pay for it. So you cannot be dust if you only limit your connections to people you already have channels with. But the issue is, if you do that, you're not growing as a node. You're not creating new connections in that network. And for Lightning to work, important big nodes need to constantly make new connections, to constantly rebalance connections, to constantly accept new incoming connections. So you have to somehow be able to scale your number of connections without degrading quality of service. Another big important scaling bottleneck is the routing gossip. This is something that consumes a lot of bandwidth because we are basically forwarding the whole graph information to every peer that connects to us. Anyone can connect to our node and ask us for the whole graph table. So that consumes a lot of bandwidth, and you want to be mindful of that. Also, whenever you validate that routing graph, you have to verify that channels exist on chain. Otherwise, you would be polluting your graph with dummy information that just doesn't make sense. And that has a cost because you have to query Bitcoin D basically to get information about an outpoint and verify that it is an unspent outpoint on chain. Also, another scaling bottleneck is pathfinding, because you have to constantly update your graph with new information and search for paths in that graph, especially if you're using something like trampoline routing. If you are only relaying payment, you actually don't need the graph at all. You receive an HLC, it tells you, I want to go to that node next, so you only have to know about your local channels. But if you're doing something like trampoline, where you are computing paths on behalf of other people, you are actually running a potentially costly graph search algorithm for every payment. So you have to do it in an efficient way, otherwise you would overwhelm your CPU and RAM. Another and one of the most important scaling bottleneck is the database read-write. This is something that fundamentally you just have a limitation on how many reads and writes you can do to a database. And that's something that I don't think implementations are very different in that regard. We are optimizing the protocol to require as few database operations as possible, but there are times where you need to store things. So here, I don't think any implementation is very different from the others. But one of the important things that that at least we do with Eclair, with database, that all analytics are never run on the master database. We have a streaming replication using Postgres with a slave database, and all the analytics are done on the slave database so that it doesn't impact the performance of a node. Because you really don't want your analytics and monitoring to be actually impacting the performance of a node that relays payments. All right, so as you know, there are many Lightning implementations, a lot of them, more every day. What sets them apart? Basically, how do you choose which implementation you're going to run if you are a node operator? I have a very simple answer to that. Just run Eclair. Don't think about it. Just run Eclair. But no, more seriously, I think that any implementation would basically work for whatever you want to do. At least if you want to run a node, any implementation would work well at the scale of the network today. So a better way of choosing your implementation would be choosing a tech stack that you are comfortable with, because at some point, if you really want to do involved things, you will have to get your hands dirty, look at the code, try to understand it, try to figure out why something you want to do is not working as you expect, try to figure out what it would cost to change the implementation, to add features that you want. So choose an implementation in a language that you know or a language that you want to learn. I think that's today the most important way of choosing your implementation. And every implementation makes different technology choices. Core Lightning is in C, we are in Scala, LND is in Go, LDK is in Rust, and there's Electrum in Python, there's LNPBP in Rust as well, and there are other more exotic things, but that are not production ready, I guess. So obviously I'm still here to shield Eclair, because Eclair is our main project. Most people know ACINQ as only the mobile wallet developers, but actually they don't. This is a very common misconception. The primary thing that we do is work on the spec and on our Eclair implementations. We've been there from the beginning of a project, and we've been actively contributing to the spec and to node implementation since 2016. We also do a mobile Lightning wallet Phoenix, but that is not our primary project. But since we are the most discrete team out there, I guess, people just don't know that. So I'm here to correct that and explain a bit what we do and why it's interesting, I think. So our tech stack. As I said, we are using Scala, which is a functional programming language. I just love functional programming. It's really nice. I'm a big fan, and maybe it's going to be annoying because I'm just going to shield it. There's a very interesting misconception about functional programming. People think that it's hard to do functional programming, that it's only for ivory tower, researchy kind of developers, that you really need to be a very smart engineer to be able to do functional programming. But it's actually quite the opposite. What I like with functional programming is that it prevents yourself from shooting yourself in the foot. There are so many things where it just helps you program more easily. Immutability ensures that it removes a whole class of bugs about mutable state. Functional programming lets you be a dumb programmer, because the compiler is going to check everything for you. It's going to help you a lot so that you can write just dumb code, because our goal is obviously not to write smart code. we want our code to be as dumb as possible. We want people to think it's easy to read. We want people to think it's easy to check for correctness and not have to focus on other things that are just not interesting to the goal of what you were trying to achieve. So functional programming is really great here. It really helps us have a small code base that is easy to read, easy to check for correctness. And then the other big technology that we are using is the actor programming model. It's something that was developed in the 70s for the telecoms industry when computers were quite slow, were having a hard time dealing with concurrent programs, and the telecoms industry needed to handle a lot of scale for a lot of concurrent connections. And they developed this programming paradigm because it really was designed for scaling reliably. It's also used today. They created the Erlang programming language to do that, if you know it. And it's used today by many companies. It's used today by WhatsApp, for example. There's a new generation of languages using the actor programming language on the Erlang VM. There's something called Elixir. And there's also a way to do it on the Scala in Scala. So I'll dive a bit more in the actor programming model because that's something people usually don't know much about. And that is the core of what helps Eclair scale very easily across machines. So the actor model is built around messages. You split your code inside actors, which are very simple, very lightweight processes, basically, that encapsulate mutable states and run in a single thread. What I mean by that is send and receive messages. So whenever you want an actor wants to interact with another actor, they're going to send an asynchronous message to that actor, which is going to land in a mailbox and at some point be handled by that other actor. And handling a message is done in a single thread, which means it removes all the concurrency issues. As long as you ensure that handling a message is always fast, can do a lot of asynchronous operations, but does not wait for the result, it makes it very easy to scale concurrently and reliably. And it forces you, whenever you make a call, send a message to another actor, it forces you to really write a state machine where you have to handle all the potential cases of what could be going wrong. Because you send a message out, you exit from your loop for your message handling, and then you have to wait for the responses asynchronously. So you have to think about all the kinds of responses that you're going to get, and also the case where you just don't get a response. So that forces you to really think in terms of state machines, and that forces you to ensure that all the cases are covered and there's no weird concurrency issue or things that you didn't handle and that fail horribly. That really helps you reason about your program in a protocol-driven way, and it's really a good fit for implementing Lightning stuff. The main goal of the actor programming principle is location transparency. What that means is that you will have many actors sending messages to each other and receiving messages to each other. And what's interesting is that they don't care where the other actors are. The other actors could be in the same process, or they could be on a different machine. And it just works seamlessly the same way. And that's what makes it really interesting and really scalable. Whenever you send a message to another actor, and the message looks a bit like a function call, basically. It means you are asking another actor to compute something interesting for you. For example, finding a path for a payment. You just send that message out, and you wait for a response. And when you send that message out, in the message, you put a field that gives the other actor your location, who they are supposed to reply to. And for them, replying to another actor that's in the same process or on another machine is handled seamlessly. The third important aspect of the actor programming model is that there's an inherent hierarchy between actors that's used to handle errors, basically. That's called supervision. Whenever you create an actor, you can decide where it runs. You can decide that it runs in the same process, it's allocated on another machine or something else. But also, there's always a root actor that's the parent of all actors. And then it's just a tree beneath of the children, grandchildren, etc. And whenever there's an issue in an actor, whenever they just crash, they just fail, and philosophy of the actor model is to just let actors crash. If there's something that's unhandled, you let them crash. The failures are going to bubble up. And the actor model forces you as a parent, when you spawn a child actor, to decide what you're going to do on failures. You can either just restart the actor with the exact state that they had and just drop the message that made them fail, or you can reset the state, or you can do exponential retries and back off, or you can just bubble up and kill yourself and let your parent handle the failure as well. So that's another aspect that forces you to think about all the ways your program could go wrong and make sure that you handle errors without degrading quality of service. So this is very briefly what an actor looks like. I don't think it's really interesting for this talk because we're not going to go into details into that. I didn't know how high level I should stay for this talk, and fortunately there's a live coding right after that where I'm going to do live coding on Eclair. So if you are interested in the gory details of exactly how these actors work in the code, just go to that event and we'll dive a bit more into it. But you can also just have a look at the code base and you will get a feel for what it looks like to see actors sending messages between each other. So the way we use the actor model inside Eclair is that every channel is a separate actor. That means every channel can potentially live on a different machine because channels are completely independent. The only thing that you need to tie them together is you need to have one place or a few places where you have a map to connect channels to peers, to know that these channels are with a given peer. But that's something that doesn't need, even with a lot of channels, that's something that doesn't need a lot of memory. It's just something that you would put in RAM on a machine that maybe has a lot of RAM if you have a very big node. But the channels can live anywhere, basically. So our high-level architecture is that there is a first actor that is a singleton that is called the switchboard, and that contains this routing map that routes requests to different peers. We have a peer is basically just a peer in the peer-to-peer network with a connection, a TCP connection to them, and they are children of a switchboard, and then each peer has a different number of channel actors. Whenever you have channels with a peer, those are children of that actor. And all of those don't have to be on the same machine. They can just be anywhere, basically. But the way we do it today in Eclair, at least on our node, we have a built-in clustering mode where you can shard your node across multiple machines. And what we have deployed currently on our node is that we have one backend node that contains most of the actors and two front-end nodes that contain those peer connections. And they are sharded between these two nodes. We actually don't really need it from a scaling point of view because there's just not enough traffic today to actually need it, but we still did it as a proof of concept to verify that it works. We could easily run on just one machine with the scale that we handle today, but we wanted to make sure that we know how to deploy this, that it just works, and that we keep the architecture of Eclair compatible with that scaling across many machines. And in the long run, we can just split everything on different machines. For example, the pathfinding actor could be on a machine that has a lot of CPU, a lot of RAM. All the channels and peers could be on very slow machine that just need a lot of bandwidth because they are exposed to TCP connections. And if they fail, it's okay. And you can even fail a whole machine and then move the actors to another machine. So there are a lot of things. This gives us a lot of flexibility in how we deploy a Lightning node. Another thing that's interesting about Eclair is that and that people don't usually know, is that we have quite a rich plugin system. Because of this actor model, any actor can basically send messages to any other actor. And a plugin has access to most of the high-level singleton actors. So plugins can send messages to almost anything in the code base and then get responses. They can also register to the event stream to get a lot of events about what's happening inside Eclair, new channels being created, new channels being closed, new connections being created. So there's quite a lot you can do in an Eclair plugin today. But the issue is, it's not really documented. Because you can do a lot, we didn't spend enough time documenting everything you can do. And our hope is that we're going to do it through example plugins that people use. There are a few big plugins that are already used in Eclair today. For example, one of the first big plugins was developed by someone outside of our team, Anton, BT Contract, who developed a plugin to do hosted channels. And he was able to build all of that on top of Eclair almost without any changes from us inside the Eclair implementation. Another big plugin that we are working on is peer swap, which we are going to put in the main repo so people can have a look at that and see examples of how we do plugins in Eclair. And there are a few also smaller plugins that we will showcase and that hopefully let people learn how to write plugins. Right. So now time for some numbers about our node. So we've been live on mainnet for 5 years. We never had a major issue on mainnet. Yes, something that I want to mention is that we really built Eclair for our use case of being able to run a big node. And that means we eat our own dog food. When we regularly deploy our master branch directly first on testnet, where we test it a lot, then on mainnet. So whenever we make a release of Eclair, you know that this code has been running on our node for a while. We've never had any issue. So that's why our releases are usually high quality, and we've never had any bug in a release, anything that really impacted users. We have a bit more than 3,000 public channels and tens of thousands of private channels, mostly with wallets, but also with other peers. We have around 350 Bitcoin liquidity. And what's more interesting from the scaling point of view is how many Bitcoin we relay per month and how many HTLCs we relay per day. As you see, this is quite low, to be honest. We are only relaying 0.1 HTLC per second. This is nothing. So that's why it's not such an engineering feat to be able to scale to that level because there's just no traffic right now. But still, we've built Eclair to make sure that whenever traffic comes, we are ready to shard the node very easily across multiple machines so that it can handle many more HTLCs per second. Our database is around 1 gigabyte. We are using Postgres. The reason why it's big, even though it's not that big for 5 years of history, is because of Lightning Protocol. Right now, we are using something called LN penalty, where whenever you add new payments, you have to remember all the payments that happened before until the channel is closed. Otherwise, someone could try to cheat you. So that means we have that toxic waste that just builds up over time. And we have channels that are 3 or 4 years old. So those channels have had a lot of activity, and we have to remember stuff for all of them. But that's something that will be made better with splicing soon, because whenever you're going to do a splice on a channel, that lets you remove all the toxic waste from everything that happened before. So that DB is actually going to shrink once we have splicing with the same number of channels on the network. And once we have L2, then it's going to be completely fixed. All right, that's all I had for you today. It's actually quite simple to run a big node on the network today. So just give it a try, have a look at Eclair. If you need help setting it up, just tell us. And if you have questions, now is the time. And if you want to see more technical details, just come to my live coding session, which is going to be, I think, in the Pleb Dev Village. And we're going to do some more internals of Eclair. Thank you.
I have about 30 questions for you, but
Perfect.
I'll kick us off. Yesterday, Matt gave kind of a cheeky presentation here that was kind of entertaining, but kind of goes over the fact that you shouldn't really be opening channels with people that you don't know. Obviously, ACINQ has the most channels. First question is, does that bother you? Is this a concern? Is Matt kind of just throwing up hypothetical, theoretical kind of issues, and maybe you have monitoring that you can, kind of protect yourself? I'm curious if you could talk to that.
No, so everything that Matt told you yesterday is real. These things exist, but we have much safer defaults than the other implementations. I think that by default we restrict the number of pending HTLCs in the channel to 50 instead of the default 483, and we're actually monitoring this actively. But we've never seen more than a handful of pending HTLCs in a channel. So we don't need to have higher limits than what we do. And this really helps mitigate how much we may lose if someone attacks us. So I would recommend anyone to use much safer defaults than what your current implementation does, because you don't need the high values that they put by default to be able to handle all the load of the network. And it actually protects you a lot to use safer defaults.
Have you guys thought of external signing capabilities, removing the keys from the node itself. And can you talk to that?
Yeah, we've worked a lot on that. And the issue is that for a big routing node like ours, where we not only route payments, but also open channels on the fly to wallet users, also do swaps, it's really hard to have the right policies because that external signer actually ends up having most of the state of your Lightning node and most of the logic of your Lightning node. So you end up wanting to run almost all of the Lightning node in an HSM. And we've been trying out many things around that, and we are going to announce some things soon-ish. I don't know when, but we're looking into it, but this is a hard problem.
So you say the database is 1 gig for you. So is that like only like channel states and all previous channel states, like invoice data or like like kind of the metadata, so to speak, is all like in an external different database?
No, it is 1 GB, but that's because we don't have payment. We don't receive payment as a node. We make outgoing payment, but we don't generate invoices. So yeah, that's why we have such a small database. Someone who would run like a custodial hub using Eclair would have to take into account the payment database. And we have a few Eclair node operators that do that. And we have one feature, for example, that automatically purges expired invoices that haven't been paid to ensure that this famous DB doesn't get too big. But one of the things that we should do here, if people actually run these big hubs, is to create DB-less invoices. Something we can do with a new payment metadata or blinded path is that whenever you generate an invoice, you actually don't have to put it in your DB until it's paid. You can put some encrypted data directly in the invoice that you give to the sender, and when the sender pays it, you have all the information you need without having to ever put it in a DB. So if people actually need that, that's something we can easily add. But right now we didn't have a need for it, and no one actually had issues with DB size. So that's why we haven't done it yet.
So I know Postgres was added like 2 years ago to Eclair. So what was that migration like moving over to that?
Okay. Oh, yeah. That's interesting. It took us a while. We took a long time to migrate because we had before that we were on SQLite. Then we added code for Postgres, but we took a very long time before actually migrating our node to Postgres, and we wrote a kind of shim that let an Eclair node run with both a primary and a secondary DB. And for a while, we ran Postgres only in a secondary DB where all the writes were replicated to Postgres on top of SQLite, all the reads as well. And we would run internal checks continually in production to verify that it worked. And we spent, I think, 6 months running our node like that before we were confident enough that the Postgres version was working correctly. And then we made the switch. And this way, you can also migrate on the fly your DB to Postgres by writing that state, even though the old revoked state you would have to migrate manually. We don't have the scripts for that. We were waiting for people to actually ask for them before adding them, but no one asked us for that. People either just start with Postgres or stay on SQLite. And to be honest, with the scale of the network today, even our node could run on SQLite very easily. So you don't actually, if you are planning to run a big node that will still be there in 10 years, maybe start with Postgres from the start. But if you are playing around and at some point you know that maybe you will migrate, just use SQLite and it's going to do the job perfectly for now as well. And it's simpler to deploy.
Hey, so today it's really obvious where Eclair kind of hits a stride in terms of like product market fit with just running like industrial nodes. In the future, when like LDK becomes much more mature, do you still see, or where do you see Eclair like sitting in like in terms of like what use case it follows? Like, are there specific like design paradigms that Eclair has over like a mature version of LDK that would still make it like usable after LDK reaches maturity?
For most use cases, I don't know how easy it's going to be for LDK to do that horizontal scaling with only one node ID. I think the approach that they chose is the phantom node, where you run phantom nodes on different machines, which also works. It's just a different way of scaling. So I think both would probably work great. It just depends on your personal preferences. If you need more way of configuring what your node does, probably go with LDK because you will have more hooks into how the node works. If you want something that's more packaged and you don't have much more to configure. And maybe if you are a corporation that's used to running big things on the JVM, it's going to be easier to plug into your ops environment to deploy on many machines to use Eclair. It really depends on who you are, what language and tech stack you're comfortable with, but both would work great, I guess.
Also, thank you. One other question. It seems like a lot of people recommend to lower the max in-flight HTLC limit, but the counterpart to that would be like it opens yourself up to a higher propensity to be channel jammed. Do you think that that's like a legitimate threat, or what do you think the trade-offs are? Are people like overhyping the channel jamming threat, and is it worth like the efficiency issues of having like a high in-flight HTLC limit?
Yeah, I agree that it makes you more prone to channel jamming, but there are easy mitigations that we can do that Antoine and Gleb identified in their research, and some of them we are already implementing in Eclair. I have an open PR for the HTLC bucketing thing, and there's also very recent, more ongoing research on how we can protect, if not completely remove, but at least protect and mitigate channel jamming. So those are things that we're going to implement. But this is definitely a risk today. You can easily be jammed today, and there's no good way around it right now in any implementation, I guess. But I think it's more important to protect your funds by lowering those limits than to be worried about channel jamming at that point.
So I have a question. So how dynamic is the connection management for the channels across hosts? Like basically if the one host dies and it has a set of connections, so do I have to spin up the same host with the same set of channels, or I can basically split those channels up into the existing online host?
Okay, so you're talking about the what we call our front-end nodes, where the connection actors are, right? Yeah. So this is really handled dynamically by our actor programming model, where if one of the hosts completely dies, we will automatically just spin up a new machine, and the actors will be respawned on that new machine. So the TCP connection will die, but it will be reestablished from another machine, basically. That's behind the load balancer, a TCP load balancer. So you don't have to do anything yourself.
Yeah. So like one way is like basically spin up a new machine with the same set of channels. Is it possible to like basically instead of spinning up a new machine, split those channels across the existing online machines?
Oh yeah, definitely. That depends on the actor allocation, actor spawning allocation mechanism, and that's something that you can configure. You can tell the actor spawning mechanism to load balance between two hosts, or to fall back on only one host if one is dead, or to spin up a new machine and load balance with that one. It's really something, yeah, you can configure depending on what you want.
If I if I understand correctly, Eclair is also using the Bitcoin Core wallet for the on-chain wallet, and it seems to me this is quite unique among the different implementations. Can you talk a little bit about what was your design thinking regarding using the Bitcoin Core wallet for your on-chain operations?
Okay, it's really simple. Is that we were lazy, because we don't want to have to write code that people already wrote. So if we could make our Lightning node work by just using Bitcoin that does all of the handling of a Bitcoin wallet, we wanted to do it that way, because we really didn't want to have to re-implement a Lightning wallet. So this is limiting in some cases, but this ensures that we have less to worry about, as long as we have a good test suite of all the behavior that we expect from Bitcoin and we're actually running that test suite every night against Bitcoin master branch to detect when something breaks in a potential new Bitcoin version. And we've been quite happy with that. So some of the things required quite complex hooks. For example, one of the things that's been painful is that Bitcoin you cannot ask Bitcoin to fund a transaction or sign a transaction if it already has inputs that are not inside the Bitcoin wallet. And that's really annoying, because that means we have code that removes the Lightning input, asks Bitcoin to fund, takes into account that we have some weight that Bitcoin did not know about, so that we tweak the fee rate that we ask for, then we re-add our inputs and sign. So this is really hacky and horrible code, but it has been completely fixed in Bitcoin 23. So once we start requiring Bitcoin D23 and onwards, we can remove those things. So there are a few things like that where we are limited by what Bitcoin D does, but we actually ask Bitcoin D, we open issues, we discuss it with the Bitcoin D team. They usually fix things, so it takes time before we can actually leverage them. But I think this is for the best, because whatever use case we need from Bitcoin D that Bitcoin D doesn't expose, other people will need them. So it helps improve the RPCs that Bitcoin D expose, and I think it helps the ecosystem as a whole.
Guys, with big distributed systems like that, usually the single point of failure sometimes comes down to the database. And I know you're using Postgres, so I was wondering how you mitigate that with Postgres for that single point of failure.
We currently don't really, and that's really, I think that's really separate from Lightning issues. That's really a standard choice of DB availability. We don't have anything very fancy right now. We are just using a primary DB and a slave replication. But if all of those go down, then we have issues. So that's something we need to improve, but we haven't found a great solution yet that's easy enough and doesn't add too much complexity to the code base. So, but that's something we need to improve in the future, sure.
I don't think there's any more questions, so I want to ask another one or two, if that's okay. Speaking of points of failure, one of your slides, I don't know if you want to bring it up, had like the switchboard, and then you had the peers and the channels, I believe. This one right here. Maybe you can speak a little bit more about the switchboard. Is that like a point of failure, and how do you scale that? And maybe you can speak a little bit about that. That's one piece I wasn't too sure about.
It's not really a single point of failure because it's just an actor. So since we talked about supervision and how failures bubble up, if that actor fails, it's automatically going to be restarted with empty state, and it's going to repopulate its state by looking at all the channels we had in the DB. It's just basically a mapping table. So it's just a plain mapping table in RAM. So if we have a horrible bug in this, then yes, sure, it's an issue. But I think you cannot work around the fact that if you have a horrible bug in your code base, then everything is going to fail. But from a scaling point of view, this isn't really a single point of failure, because you can even spin many of them, have a primary and a slave mechanism for that, and just switch to the other one if one fails.
Okay, and here we have one right here.
For like an average user that might want to run the node, can you describe like a backup methodology and a workflow compared to what everyone's usually familiar with from LND, the static channel backup?
Okay, so here what you want to do is to back up your DB. With SQLite, we have different ways of backing it up, where going from either a full copy of the DB that's made at every update or just regularly. And for Postgres, you should just set up streaming replication. That's a built-in Postgres mechanism where all of the writes are replicated to a slave DB. And that's also really useful because it lets you run the analytics on that DB. That DB can just be read-only for analytic demands, so that analytics can pull data from the slave DB without impacting the node and provide you with real-time monitoring and analytics. So if you want good backup, that's where Postgres shines compared to SQLite, yes.
My last question is, you're mentioning right now the state of Postgres for your node is, or for the ACINQ Eclair backend node is about 1 gigabyte right now. You're mentioning splicing, L2 could even bring that number much lower or lower. But I think kind of piggybacking off of Graham's question, you mentioned all the numbers and all the HTLCs and stuff. Why is it that when I run different implementations, the DB size is way bigger, right, than 1 gigabyte, having much less volume?
But is it really bigger now with other implementations? Because I would expect Core Lightning to have the same size, because I think we store the
maybe
same
like
things.
LND specifically.
But LND before, I think it was before .15, because before .15 they were storing a lot of useless information, whole payment onions basically, that you really didn't need to keep. But I think they fixed that recently, so nowadays you should not have the same issue with LND. I think LND should be able to have the same DB size nowadays, but I'm not sure.
Is there any other questions? Okay, thank you so much.
Thanks.